My name is Aaron Cummings, and the title of my talk is Making Memories, Clojure for Engineers and Others, and I think it'll be clear what that title really means as we get into things here in a couple of minutes. I've been programming in Clojure for about 5 years, and this is my first time speaking at the Conj, and I'm really excited to have this opportunity. So the idea for this talk was sort of based on some conversations that I've had here at the Conj in previous years. And I talk about some of the things I'm doing at work, which is, well, I'm using Clojure to make embedded memories that we put into custom logic chips. And folks would be just totally blown away that you could even use Clojure for such a thing. So we'll get into how that works here in a couple of minutes. But first I want to start off by talking about software and data and computers and memories and a little bit of history. So here's the obligatory definition slide. What is the definition of software? It's the programs or other operating information used by a computer. And what is data? Data being the quantities or the characters operated on by a computer. And I think there's 2 points I want to make here. First, I assert right up front, software is data. The second is really more of a question. Is data really the opposite of hardware, as it's said in the dictionary? And we'll leave that question open for a moment. So here's what our computers look like. These are the types of machines that we run on, at least at a very abstract level. These are stored program, digital, electronic computers, and there's 5 major components to these. There's input and output devices because we want our computers to have some interaction with the outside world. There's a central processing unit which has a control unit and an arithmetic logic unit. And inside of that we talk to a memory, which is where we store our programs and our data. Now, when we started off with computing back in the 1940s, everything was literally done by hand. The schematics were drafted by hand. The chassis that the computers were made up of were wired by hand, and they were made out of discrete components, vacuum tubes and resistors and capacitors and relays, and they were huge. This is ENIAC. This is the first general-purpose electronic computer. This machine came online in 1945, and this computer had no stored program. There wasn't any memory to store your program. Instead, it was literally hardwired with plug boards and switches. And actually, if you look at the Wikipedia page for ENIAC, the word software doesn't show up any place, but although it does talk about programs. The first stored program computer, and this is where you start to get something that looks at least in the same architecture of what we deal with now. This is the Manchester Baby. This came online in 1948, and it had enough memory to store the programs that were running on this machine, which was 1,024 bits, 1K bits of memory. And that memory is stored on one of these. This is a Williams tube, and this is a cathode ray tube, and the memory is stored as a matrix of dots that are printed on the front of the phosphor on the CRT. And that matrix of dots represents the ones and zeros, and those are then sensed electrostatically with a device that's attached to the front of the tube. This is core memory. This came along a few years later, largely replaced the Williams tubes by the mid-50s. Each of these iron toroids would hold a single bit of data magnetically, 1 bit per toroid, and it was, you could achieve great densities of 32 kbits per cubic foot on these little iron donuts. This memory actually lasted quite a long time. This is around for probably 20 plus years and was used on some of the early Unix systems like the PDP-11. And so when you talk about core memory and your program going bad and you get a core dump, this is where that term core is really coming from. Now, through the 1950s, computers got smaller and smaller. The vacuum tubes got replaced with transistors. Those hand-wired chassis were replaced with printed circuit boards. And this is some modules from 4 machines. This is a timeline from about 1945 to 1960 with machines that were running at the U.S. Army Ballistics Research Lab. These are modules from left to right: ENIAC, EDVAC, ORDVAC, and the Burlesque machine, which came online in about 1960. But it wasn't about 1960 that we saw the really big step forward and things start to move along pretty quickly, because now we have integrated circuits. All of the components of your machine are printed onto a single silicon substrate, and they're printed on there using photolithography. In 1964, the first commercial metal oxide semiconductors became available. Metal oxide semiconductors are still the basis of the chips that we're building now. Gordon Moore in 1965 published his observation that the number of components on an IC was doubling every year. IBM invented dynamic RAM in 1966, and in 1968, Viatron Computer Systems. Has anybody heard of Viatron Computer Systems? All right, let's talk later. Viatron in 1968 coined the term microprocessor. That's really their great contribution to the history of computing. Now, by 1974, core memory is on its way out because dynamic RAM is now cheaper to manufacture than core memory. This happens to be a picture of a board that I have at my house. This is a memory board from a Data General computer from the late 70s. And it's 12 inches by 12 inches, and it's just loaded with these DRAM chips. Now, semiconductor manufacturing, it's photolithography, it depends on photomasks. And really, for quite a long time, those photomasks were still being made by hand. This is a technician from the Air Force modifying a photomask, the master of that on Rubylith. This photo is from 1980. So this manual process really went on for quite a long time. But then something changed, is our computers finally became powerful enough that we were able to use the computers as the tools to design computers. And that really became the genesis of an industry which we call electronic design automation. And EDA, you have hardware description languages like VHDL or Verilog. Those take your high-level design, synthesize that into logic gates. Those get placed, the wires get routed. You do all of the analysis and checking to make sure that all of the shapes are going to print correctly. And at the end of all of this process, your entire design at this point really is data. It's data which is then going to be mechanically converted into those photomasks rather than doing things with tape and razor blades like this. And so now for the last 4 decades, this is really the situation that we have. This is our world. We have hardware that executes software, that generates data, that then fabricates hardware. And if software is data, well, maybe hardware is data too. And so this is it. It is really now that we've bootstrapped data all the way down. And because hardware is data, we can use any programming language that manipulates data, just like Clojure, to help us out with our hardware designs. Okay, part 2. I work for Global Foundries. We are a leading full-service semiconductor foundry, and we provide chip design, development, and fabrication services. This is my team's motto. We design memories that are embedded in custom logic chips, and let's take a look at what those memories look like. This is the IBM Power 5 processor. This came out in 2004, and I chose this particular picture for 2 reasons. One, it's really pretty, but it's also really easy to see the memories on here, and I'll take and highlight those in orange. And one thing to notice is that each of these is built to exactly the size that you need for whatever the application is. And I mean, you don't want to build and burn more silicon than you have to. This really is a custom design process. To see what memories look like as data, let's build one. And so this is going to be sort of a toy design. It's not complete. You can't really go to silicon with this. But I think it does demonstrate at least what this might look like in Clojure. So we'll build a single port SRAM. This has a single read-write port, and it's pretty small. It just has 12 words and 8 bits per word. The way to think about this from a software standpoint is it is an array of bytes. And there's 12 bytes in this array, numbered 0 through 11, and one operation at a time. You can either write it or read it. Physically, it looks something like this. And let me turn on the pointer. There we go. And so there's 4 major blocks to this memory. First, there's the bit cells. We have 12 times 8, or 96 of those. That's where our 1s and 0s are stored. There's a data I/O section, and that's going to be what gets the data in and out of those bit cells. There's this word line decoder section, and that word line decoder, that is what selects one of the 12 rows of the memory. And there's a control section here with some clock generation circuits to get all the signals to happen in the right order. And so here's some Clojure code, a snippet of what our designers actually write in Clojure now. This is just a thread first block. Start with an empty block and then place inside of there the 4 top level blocks that we saw here. Now this is like a sort of a turtle graphics program for placement. You start at an origin, you place a thing, you walk to the next thing. You might be able to warp the turtle around because it needs to reset back to the origin, perhaps. And this really represents, what the physical assembly of the memory looks like. Now, when we put these blocks next to each other, what's not shown is there's wires that are in each of these blocks. When you place these blocks next to each other, the wires abut. They do make electrical connections between those blocks. And something that I've left out here is we need to also put in a description of what those electrical connections are supposed to be, because that's used as part of the checking before we go ahead and build this. So this code ends up returning a data structure that looks something like this. And so we have a block, it has a name, it has some instances of where things are physically. This would also have a description of what the electrical connections are, which is basically just a Clojure map of what connects to what. And so what we end up with is a memory that looks like this. Now, I just looked at the top level. The truth is there's hierarchy underneath this with individual placeable blocks. And I put some lines in here to show what the leaf cells in the hierarchy would look like in this toy design. Couple of things to note here. I picked a size. It was sort of hard-coded in here, but clearly it's Clojure. We can parameterize it. It means that we can build, within physical limits, any size memory that we would like to do here. So that's the context and a little bit of background on computer hardware and what hardware might look like represented as data. But this isn't really the entire point of the talk. What I really want to do is, what we did with our extended team at Global Foundries, and try to use our experience as a proxy for kind of a bigger question, which is, how can we enable folks who might be engineers, they might not be engineers, how do we enable people who could benefit from Clojure, some sort of programming in their jobs in order to be able to do that? And what that might look like is, maybe it's a configuration of some larger system, which is really what I'm presenting here. Or maybe you need something that transforms data from one form to another. Maybe you need some glue code that puts systems together. So going forward, I'm really talking about what our shop is doing with Clojure, but I hope that there's some ideas here that are broadly applicable. So Our design teams, what is it that they actually do? Well, they have these inputs. They have requirements of what it is that you're trying to build, and then the components that you have from your silicon vendor that, these are the pieces that you can build from, the models for your devices and the rules of how they have to be built. And what they then generate is a detailed design. And that design includes the leaf cells, the sort of maybe a hand-tiled configuration, which is used for exploratory purposes. But ultimately what comes out of that is an understanding of what your hierarchy is, how things get placed, and an algorithm which describes how things are going to get placed as you parameterize, as you grow the memory design to different sizes. And so the topology of the team and the data flow of the team, it could look like this, where the design teams are not writing any software and instead just write a spec. It's like, okay, here's the pieces, here's how they need to fit together, throw that over the wall to some programmer who's going to implement everything. Now there's a couple of problems with this. One is that the fellow at the end of this is a funnel through which all of the data is flowing. And it's also anti-agile in that the design teams are throwing something over, they're waiting maybe an entire day, maybe longer to get the data back, and so this adds to a really long debugging loop. With that kind of structure, the design teams these are folks who just want to get things done. If they don't have a solution in hand, they're going to invent their own with whatever programming language or making their own systems, regardless of what a greater vision might be. And so this is the structure that we would really like to move to here, which is to get everybody on a common environment, a common system, have some coherence in how things are getting done, sharing and reuse. This does change the role of what's on this chart as the front-end team. Instead of being somebody who is doing all of the programming, you're really enabling the upstream design teams to do the programming. Now, we originally had a situation that looked like this, and this went on for a while, but clearly wasn't sustainable. So we did eventually, years ago, enable our design teams to have this kind of arrangement where they were writing their own memory tiling algorithms, but they were writing it in C. And this is a system that we had for a long time. It was a global mutable data structure that described the memory, and this was okay. There's things about it that actually worked pretty well. First of all, it's something that worked. Don't underestimate the value of software that works in corporations. Some of this code had been written 25 years ago. It was fairly memory efficient because it had to run on machines that were 1990s, 32, 64 megs of RAM type hardware. And I put easy in scare quotes. It was easy because there was already a lot of material that was built. Folks tended to build new designs by mapping them from previous designs and then making some modifications. And so there was the near at hand aspect of this, but there were certainly things that didn't work real well. We had folks who weren't Dennis Ritchie writing a lot of C code. A lot of the C code was having to name things, and so we were bashing strings with the standard C library, which ran into memory management problems. There was this giant global data structure that was really hard to visualize, so it was tough to figure out if your code was behaving badly, what was actually going on. And ultimately you ended up with this giant mud ball of code that really looked nothing like your original design structure. As well. So let's step back for a second. And the question here is there a way that we could make the code more structurally resemble the problem being solved? Because you can take this apart into blocks, and each of the blocks is something that has a name, it has things that it depends on, it has some parameters that it takes that describe how it's going to grow. And then there's some placement and connectivity information. And so if we're not going to write this in C, do we write our own domain-specific language? Well, that's a ton of work. Language design is hard. You need to build up a lot of your own tooling. And given that I'm trying to replace a working system, this needs to have value pretty quickly. So this is really going to take too long. How about a data format? I mean, certainly with the toy design that we showed, you can imagine that you could write just a simple data format that would describe that, and you could put some parameters in there. But data formats always turn out to be not sufficient enough to really get along with the real world. Greenspun's 10th rule says if you have a system that's complicated enough, and we all do, you're going to get some sort of half-baked language built into it. So let's skip the half-baked language and pick a language that already exists. And if we're talking Lisp, let's just go ahead and do Clojure. So this is how we're going to go forward here. So my design teams had heard that I was up to something, and they were a little bit apprehensive about it. We had a couple of our remote teams on site. We were in a meeting, and I finally announced, hey, we're going to re-engineer the memory tiler system. The response I got was, we're still writing in C, right? No, I've got this Lisp that runs on the JVM. It's awesome. Okay. Because everybody has bad memories of Lisp. And this is what they remembered. But parentheses aside, it's like, are parentheses really the problem? And so if you look at programming styles that folks have seen, this is C-type languages, shell script, Tickle, and Lisp-type languages. There's about the same number of delimiters in each of these cases. You're looking at commas and white space and semicolons and parens, and maybe you have new lines because you need something that separates your pieces and tells you where the beginnings and ends of things are. And so, going from, say, C or Perl, which a lot of folks had is just move the paren to the left of the verb, and you'll be okay for function calls. But then there's the grumbling about math. And this is where Lisps are extraordinarily consistent throughout the entire library, in that everything is functions, even things that are considered to be operators are functions. This is something that you can talk through, and we found that this wasn't really a problem other than there was a little bit of, what Jabberwocky is this at first. Turns out there's not really a lot of math to write in these operations, so this turns out to be not too much of a problem. I tripped across this quote from Marvin Minsky the other day. If anyone could learn Lisp in a day, unless you already knew Fortran, and then it would take 3 days. And so it's like, well, why is that? And I think to understand why that is, we need to get back to what is it that is our model of computing? And it's this, and we have memory. And that memory is a place that we put things. It is, again, like Rich said, it's place-oriented programming. And our programs declare places, and they manipulate values and poke at those places. Your CPU, if you're writing on assembly language, this is all about testing things and poking values into places. C really isn't a whole lot different than this. Another language very much of the same kind of paradigm of putting things in places. And then if you look at Java, it doesn't look a whole lot different here, right? So here's a function. This is something that takes in a list, it returns a list, and it runs some operation on each element of that list where we're adding 10% to all of the numbers in the list. And you take somebody who's programmed in Java or in C, and you say, well, translate this to what you would do in Clojure. And then you end up with something like this. And you go, oh, don't use that def thing inside of a function because that's not really where you want to go. So, all right, Google. Okay, with local vars, that must be the way to do things. Now there's like 4 or 5 closing parens on here. Maybe there's something going wrong with this. Well, here's another function. This is looking for the maximum element out of an entire list. And this is the literal translation of that. And oh yeah, there's the with local vars thing again. What about the magical powers of this Lisp you were talking about, Aaron? I mean, this is terrible. It's bigger, it's hard to understand, and there's 30 parentheses in here. So we'll get back to that in a minute, but this was a thread that showed up on the Clojure subreddit back in September. How does anyone learn this? And this really resonated with me quite a bit because it really, I could feel for the fellow who had written what kicked off this thread, because it reflected my own experience in trying to get started with Clojure, and really I saw a number of folks on my team struggle with these same things, and there's a lot to unpack in here. There's talk about making a shift of mindset. The word paradigm shows up 10 times. There's some book recommendations, but the really worrisome part is with the mindset shift, it might take weeks or months, maybe years. I don't have that long because my project is in big trouble and we're still going to be writing things in C forever. There's a couple of really nice posts that James Reeves had put on here. One was a recognition that reduce might be an operation that you want to use. I wish I had seen this post 5 years ago when I was learning Clojure, because there was the how do I bash data in place without mutable things, and of course this is one of the ways that you can do that. And there's also this insight that maybe there's something about just this idea of always wanting a place to store your stuff. And that's something that's kind of tough to get over. And I think this idea of storage as part of the mindset shift is really one of the toughest things to get about getting started with Clojure. It's not functions or syntax or the library or dynamic types or anything else. So, a couple of words about immutability. With immutability, you're really taking away something about how the computer fundamentally works, and this ends up being a really tough sell to folks. If you hang around and you watch enough Clojure videos, you do get the concept that, yes, immutability is the way to go for a lot of things. And I'm not going to give that sales pitch here. I'm actually going to go just the opposite and talk about mutability in one slide, actually one tweet. And I want to thank Jim Dewey for this one. In other news, mutability sucks. I would love to hear the story from Jim sometime about what kicked this off. And also, I want to give Steve Miner the award. He wins Twitter for this response. Some things never change. Thanks for that one, Steve. So we need some tools to help us deal with immutability. One is a recognition that there's idioms that we've written in languages like Java where we iterate, that there are non-for loop replacements for those in Clojure. Like our add 10% function is really just a map function in Clojure. Our max function that we had written in Java, that can be just brought down to a single reduce. Threading that we might have within Clojure, this is a little bit tougher to look at coming from Java. Maybe there's a parallel here with streams. But for this, I reach back to Unix. And so let's say I'm going on Wheel of Fortune. I want to know which vowels I'm supposed to buy. So I put together a series of pipes in a Unix shell to take the dictionary and then count the vowels that are in the dictionary and then sort them by number. And this is I think this is a really powerful mental model, at least for me, in learning Clojure and thinking about threading and then lazy sequences that were between the functions in the threads, because this really just literally translates from shell script into Clojure pretty cleanly. Now, there's sort of a paradox here in that the folks who are really experienced in Unix systems, completely understand this translation, but they're also the folks who got most tripped up by the immutability. Now, back on our memory design, this is a portion of what makes up a single hierarchical block, a description of that block inside of the memory. And there's some other code up here. There's a let block and some boilerplate for the def end and things like that. But this is what we are asking our upstream teams to write and to learn just enough Clojure that they can do this portion of the job. You know, we have our turtle graphics placement of the subblocks, and there's a few other things going on inside of this thread first. But I think the real key is we are giving our design teams a very focused view of Clojure. You know, with that Clojure, with that focus comes clarity, and that clarity is, you know, you can now solve at least, you know, a specific problem using this language in almost a DSL-like way, but without all of the baggage that comes along with your own DSL. So, I mean, what's really going on here is you have a hierarchical block, you write a function, we sort of give a template for what that's supposed to look like. And what that does is it, you know, works on a data structure with calculating some things in the let, applying this thread, and then it returns a data structure which describes the placements of the interior blocks plus the connections between them. And that's it. That's what we're asking the upstream design teams to do here. And this pattern repeats, you know, all the way throughout the hierarchy, all the way to the top of the memory. Also related to focus, Clojure Core is a pretty big library. If you look at the cheat sheet, it can be kind of intimidating because there's like, oh my gosh, there's a lot of stuff on here. There's 651 public symbols in Clojure Core. I did go through and look at every symbol that was used from Core in all of the code that my upstream teams wrote. There's only 58 that they actually used. And the concepts within the language, it was really vectors and maps and keywords. There's some threading in there. There's lets and def ends, and some anonymous functions in there as well. This is actually the complete library of everything that managed to get used. But what's really most interesting is what wasn't being used. And the list of things that you can ignore in the language when you're trying to enable somebody who's using this as a focused task is actually it's a pretty big list. Now my front end team is using a lot of these techniques, of course, as part of the enablement. But for folks who aren't writing Clojure all the time, we're able to leave a lot of this stuff out. Couple more items here before I wrap up. First, I think it's really important to write examples. Folks have a sort of an ease with the original system because they had code that was lying around that they could then adapt for later designs. We did start this project as part of our rollout. We took a couple of the memory designs, wrote complete implementations of what they would look like if it did this in Clojure instead of in C, and then handed that off. That helped us discover what had to be done, but also gave our design teams a template of what a complete working system looked like. Read the code that you are receiving from the upstream teams, and you're going to learn things mostly about how you are teaching your folks who are upstream, and this can lead back into better training and better documentation. Not just reading code, but observe people work if you can, because this will tell you how workflows are getting put together, or if folks are getting tripped up on how to interact with the REPL, or finding things, or maybe using some external editor which is their favorite editor and then trying to push that into the REPL and not getting the advantages out of the REPL-driven development. Our teams are spread all over the planet. I don't get an opportunity to meet with them at convenient times for everybody, so we try to record some of our training and post that online, at least internally, for them to get access to. This is especially good at trying to demonstrate workflows. If you do this, get a good microphone, a quiet space, and make some videos, short, focused tutorials. This is actually so easy to do now. It's really helpful. And also don't let people have to build everything on their own from scratch. Give them the scaffolding where they can start working right away. And for this, we installed Cider. We got the right version of Emacs that we wanted folks to use. We set up all of the profiles and put together a document. It's like, here, grab this stuff and just run it. And so they aren't running out to Melpa and trying to download things and debug what's going on with that. If you're dealing with teams, especially those outside of engineering, you might find that they don't really have acceptable version control systems, at least not acceptable to software folks. Find some way to get them on a common version control system with everybody else. This helps tremendously with collaboration, and it really becomes the mechanism for handing off data from one team to another. You should always do data handoffs through a version control system. All right. I think I'm okay on time here, so here we go. Last part. So we completed our designs. The design teams, we got positive feedback on this, and this project was really considered to be a success. Compared to the previous incantation of the system, the code is simpler and there's less of it. It's still fast, and we did build this into silicon. This is a picture from Wikipedia. This is not one of our wafers. It turns out that I can't take pictures of products at work. But just trust me, we did build them, and we tested them out in the lab, and they worked. So going forward, we've certainly learned a ton here. Guy Steele said if you give someone Fortran, he has Fortran, and if you give someone Lisp, he has any language he pleases. And what I really take from this is, yes, we've put together this first iteration of this project. I think there's some boilerplate things that we can improve on the next iteration that we're planning now. And I think we might find some way to use macros to make the system even more declarative than it is. I would like to see the teams who are interacting with Clojure really embrace the REPL more than they have, and this is something I have. I think it gets back to the training and demonstrating workflows. That's was really more aspirational than something we've actually gotten done, but clearly that's something that we should do. Data visualization, we're working in a physical kind of visual medium. We're working with folks who work with things visually. We want to be able to not just show data structures, but have some way to visualize those. And I'm kind of inspired by the Rebel talk yesterday, and of course, training that we would like to continue to improve. So I'd just like to send out a couple of acknowledgments to my extended team who has joined me on this journey and been so eager to adopt these new ways of doing things. And a special thanks to Daryl Hill, who is a programmer on my team. He's actually written most of the code that lies underneath this, and he's been listening to my ideas for the last couple of years and going ahead and making those a reality. So that's it. I'm actually right at time here, so if you have any questions, come find me. I'll be here for the rest of the conference. Thanks very much.